So in this problem, we're told that two speakers, speaker 1 and speaker 2, are separated by a distance 6.60 meters and are emitting sound at the same frequency, 44.0 hertz, but are going to be exactly pi radians out of phase with each other. We're asked at what distance along this line between them is the sound going to be the most intense. And so we've defined position, in this case, with our origin at speaker 1, so position 0 at speaker 1 and increasing towards speaker 2. This is sort of an arbitrary construction. We could have just as easily defined position in the opposite direction, starting at speaker 2 and increasing towards speaker 1. It doesn't really matter because the situation is symmetrical, but this is just how we've defined it. So in order to solve this problem, first we're going to note that if the two speakers were in phase, they're not, but if they were, then the two waves would meet at the very center exactly in phase with one another. So what that means is that two waves that are emitted from different points, when they've traveled the same distance, so long as they have the same frequency, will always be at the same point in their phase. And so what that means is that at this center point, the two of them have both traveled the same distance, 3.30 meters, and that means that they'll always have the same phase at this center point, which means that that'll be the point at which they can reach their maximum, because both of them will, once every 2 pi radians, reach their maximum, and so then they'll reach the maximum at the same time, and so this is going to be an antinode. So if this is an antinode, we of course know that this is also an antinode, and so the distance exactly halfway between them has to be a node. So this is for the case where the two speakers are emitting sound in phase with one another. Now if they're out of phase with one another, and one of these is shifted over pi radians, then we're going to get a situation that looks a little bit different. It's going to look something like this. So if this is shifted over by pi, then the two of them are going to cancel out, and what's going to happen is that our nodes and our antinodes are actually going to switch positions. So instead of having both waves always in phase with one another at the center point, what's going to happen is the waves are always going to be exactly opposite each other's phases at the center point, because they've traveled the same distance. They started exactly out of phase, and so then they have to meet at the center exactly out of phase again. So that tells us that this is always going to be a node, since the two waves are going to cancel each other out, which tells us then that this is going to be a node, and by the same argument as the in-phase example, this point halfway between them has to be an antinode. And antinodes are the points at which the sound is most intense, because it reaches the highest amplitudes on either side. And so all we need to do now is find the positions of all of these antinodes. We can do that by doing some calculations with the wavelength. And since we know that the node is at the center, all we have to do is shift those positions a little bit, and we'll get all of the antinodes, and thus all of the answers that we're looking for. So first we need to find the wavelength. We know that v, the speed of sound, is equal to nu times lambda, which tells us that lambda is equal to v divided by nu. So that's going to be 330 meters per second divided by 44.0 hertz, which gives us 7.5 meters. So now if the distance between an antinode and an antinode is lambda over 2, and of course that's the same as the distance between a node and a node, then the distance from node to antinode has to be lambda over 4. And so that's going to be 1.875 meters. So now what this tells us is that we can find the position of an antinode by simply taking the known position of a node at d over 2 and adding the distance from a node to an antinode, and so that has to be an antinode for these two sound waves. So now we can extrapolate from this and use it to find the position of any arbitrary antinode that is produced by these two sound waves along this horizontal line. And so all we need to do to find that is add in any integer multiple of lambda over 2. Since we know that antinodes are separated by a distance lambda over 2, if we take this known antinode, and if we add any integer multiple of lambda over 2, we're guaranteed to then find ourselves at another antinode. So now any distance that fits this formula is going to be an antinode. As it turns out, there are only two distances that are in between speaker 1 and speaker 2 that fit this formula. All other antinodes are going to be either to the left of speaker 1 or to the right of speaker 2. And so the values that actually work for this are going to be n equals 0 and n equals minus 1. And so then our positions for our antinodes are going to be d over 2 plus the distances between a node and an antinode, which is going to be 3.30 meters plus 1.875 meters plus 0 in one case, and then in the other case, 3.30 meters plus 1.875 meters minus lambda over 2, so minus 3.75 meters. So these give us our final answers. This is going to be 5.175 meters, and this is going to be 4. I'm sorry. This is going to be 1.425 meters. So these are going to be the positions in between the two speakers at which the sound has the greatest intensity.